Okay, we're now in Module 3 of Chapter 12, which is going to discuss the so-called Greeks. The Greeks are a collection of symbols used to describe the price sensitivity of options to changes in various parameters that determine that option's price. So we've already encountered delta. Delta can be defined as the change in the option price when the stock price increases by $1. Intuitively, one can think of it that way, and we can also think of delta as a derivative. Delta is in fact a derivative of the option price with respect to stock. That's what a delta is. And then it's logical that if delta is this derivative, that if the stock price, if delta S is 1, the stock price changes by 1, the option price changes by approximately delta times 1, namely delta. So delta can be thought of as the change in the option price when the stock increases by $1, or we can think of it as a derivative. Gamma is the change in delta. So we can think of gamma either as the first derivative of delta with respect to S, or the second derivative of the option price with respect to S. We'll see these formulas a little bit later. But again, sometimes people go directly to thinking of gamma as being the second derivative of option price. Vega, which is actually not a Greek letter, but is often denoted with a V, and sometimes looks like a script V or a nu in Greek. Vega is what happens to the option price when volatility increases by 1%. And I'll talk later about the convention. But here, if one defines the derivative of the option price with respect to sigma, this is what happens to the option price when sigma is defined in decimal units. And what people often want is what happens to the option price per 1%, where the units are percents. And so you'll find in many tables that vega is defined as 1 over 100 of this derivative. So then a vega occurs for every 1%. Theta reflects a decrease in time by 1 day. We know that the price of an option depends on the term. We saw this in the very first module. And so the question becomes, on average, or right at this moment, how quickly will the option be changing its value simply because of the passage of time? That's what theta is. But notice that theta is a measure of decrease. So if we're going to define theta by a derivative, we would define theta as negative the derivative of the option price with respect to time. That way you get the change when time decreases. Rho and psi are now defined in terms of option prices where the interest rate changes, that would be dO d rho, or where psi is where the dividend changes, dO d delta. And what one finds is that you always have to be a little careful about the units. The three measures you always have to be careful about in using are vega, rho, and psi. And the reason is that the convention I mentioned a moment ago about vega, where the illustrated values of vega will be 1/100th of the derivative value, because then you use them with units of percents. That's often the case. The author makes this note. You'll notice with rho and psi, by 1% is the quote, or what happens per 1%. So in neither of terms, we can express all of these Greeks as derivatives or partial derivatives, because the option price is a function of several variables, so they're technically partial derivatives, but they're simply the derivatives of price with respect to these variables. Notice only one, that theta has a negative. It's the negative derivative because we're interested in a decline in time. And the other ones to note is to be a little careful about vega, rho, and psi, just simply because of the numerical convention as to when one determines the effect on price, are the units of sigma decimal units or percentage units? How does one do that?